Okay, so without further ado, I'm going to introduce Dante Lauretta, who I'm sure everyone knows, but it's worth going over some important info first. So Dante got his Bachelor of Science in Physics, Mathematics, and East Asian Studies from the U of A in 1993, and then completed a PhD at Washington University, St. Louis in 1997. He then went on to do a postdoc and was an associate research scientist at ASU until 2001, and then came here and has worked his way up from an assistant professor to associate to full professor, and then in 2021 was promoted to a Regents professor. Dante's interests are broad, and before his mission involvement, he was very active in cosmochemistry and experimental petrology, with a particular focus on the formation and evolution of sulfides in meteorites and their respective parent bodies. And I think that's in part what garnered his interest in astrobiology. And if you don't know, Dante helped to establish the Arizona Astrobiology Center, the AABC, here at the U of A, and is the director for the AABC. Okay, so of course, Dante is well known for his role as PI of NASA's OSIRIS-REx mission, which is what he's going to talk about today. And he's held that role since the passing of former LPL director Mike Drake in 2011. And so today, Dante is going to give us all a very big treat and give us an insight into the initial analysis of OSIRIS-REx samples, which is about a 20-year in the works, making for trying to get these sample analysis. So over to you, Dante.
Thank you, Jess. Thanks everyone for coming. Let's jump right into it. It's exciting times here at LPL in cosmochemistry, sample science, small body science, and asteroid exploration. So let's just start out with the background. OSIRIS-REx, a NASA mission in the New Frontiers program. It's New Frontiers 3. Target is sample return from a carbonaceous asteroid. We started this work at almost exactly 20 years ago. Early February of 2004 was when I was invited onto the program, really to begin proposal work with selection in 2011. The name captures the principal scientific objectives of the mission. We're very interested in origin science, origin of the solar system, origin of the Earth, especially habitability, and origin of life. We're trying to understand if carbon-rich asteroids, like our target Bennu, may have delivered essential compounds late in planetary accretion, like the water that's in our oceans, the molecules that are in our atmosphere, and the carbon and other key elements that make up biology. We are interested in spectroscopy, and we'll talk a little bit about spectral results. The fact that we returned a sample from the surface of this asteroid allows us to ground truth the telescopic data as well as the spacecraft-based remote sensing data. We're interested in asteroids as potential resources. We worry about them as impact hazards. And we are the regolith explorer, regolith being the loose blanket of gravel and dust that covers these airless bodies, that we documented the location where we collected the sample from down to sub-centimeter pixel scales. And of course, we now have it in the laboratory. Here's an overview of the operations timeline of the program. You've probably seen a lot of our commemorative posters. We have the complete collection now with sample return in 2023. We put one out every year since 2013. And these are the operational ones. We launched in September of 2016. Because Bennu is inclined, you'll see the orbit diagram here in a little bit, inclined by 6 degrees relative to the ecliptic, we came back to the Earth after 1 year for a gravity assist, which allowed us to make that inclination plane change. And then we began the approach in late 2018, spent all of 2019 mapping the surface in exquisite detail, ultimately selecting a location, which we sent the spacecraft down in October of 2020 to collect that sample, leaving the asteroid in May of 2021 and returning the sample or delivering the sample to the Earth in September of 2023. So we're now in the very last phase of the prime OSIRIS-REx mission, sample analysis, which is currently slated to go through late 2025. So we're just getting started really on the science program of this mission, which has been in the works for a couple decades. Here is the target of the mission, Bennu. It's about 500 meters in average diameter to give you a sense of scale. It's got that really interesting spherical spinning top shape. By the way, I saw it pop up on a trivia question on a Netflix game show. Worth $500,000. What is a giant asteroid Bennu shaped like? Was the question. You got it wrong. So just keep that in the back of your mind. A spinning top was the answer, as opposed to a peanut, a wisdom tooth, or a pocket watch. I think were the other options. He guessed peanut, which I can understand, having seen Itokawa and other small bodies that do have that shape. If you're guessing, that's not that one. Over here, you can see the orbit, Bennu in blue, Earth in green. And you can see that it is an Apollo-type near-Earth object, meaning it crosses the orbit of the Earth. You can see that 6-degree inclination from this side view here. And Bennu does a close approach approximately every 6 years. It's on a 1.2-year orbital period versus 1 year for the Earth, so they come close to each other every 6 years. And that kind of drove the mission timeline. After that extensive mapping campaign, we selected this region of the surface called, we nicknamed Nightingale. It's in a 20-meter diameter impact crater named the Hokioi crater. Very interesting site. Most of the surface, if you follow the saga of OREx, kind of looks like this outer area here. This is about a 12-meter tall boulder we called Mount Doom. You can see from its shadow how tall it is right on the southeastern edge of our target location. Other large boulders all around. But this area really stuck out because it appeared to have fine particulate material dominating its surface. You'll see the sample collector, what we call the tag SAM, or the touch and go sample acquisition mechanism, that can pick up particles about 2 centimeters or smaller. And so we needed to find an area of the asteroid surface that had particles of that size. And this was one of the few relatively accessible areas. It was safe in the sense that even though we had these giant boulders around, our guidance accuracy was allowing us to target the interior region here. There were some spacecraft killing boulders. These are about meter scale boulders nearby. And we had to upload and make the spacecraft recognize these as hazards. And as it was descending for the final collection, it was predicting where it was going to make contact. And if it had predicted contact near one of these hazards, it would have backed away and come back to sample another day. So navigation and safety all checked out. Bennu is generally a blue asteroid. I'll show you the spectral data a little later on in the presentation, meaning that it has higher reflectance as you go to shorter wavelengths, even into the ultraviolet. The crater was redder than the average surface. And as we looked at that distribution of surface reflectance as a function of wavelength, and our own Danny Della Justina, who was the image processing lead for the mission, wrote the paper on this. These small craters definitely have the trend of being redder than the average surface. We think they're younger. Small craters are typically younger features. When we look at objects in this 20-meter size and smaller, they all look pretty red relative to the background, a blue asteroid. And the size distribution of those craters is consistent with the near-Earth impact population, suggesting that these craters were formed over the past 100,000 years, that crater population. So that's very young compared to the estimated age of the asteroid, which we put at about on the order of 1 billion years, I think 800 million to 1.5 billion. It's part of we think, an asteroid family. We look at the inner main asteroid belt. We see the Eulalia population, the New Polana population. Those were formed in a giant catastrophic impact in the main belt. And we think Bennu was a fragment of one of those. So as an object, it probably formed roughly 1 billion years ago. This crater is part of a population that looks like it formed over the past 100,000 years. So a very nice young area. From the spectroscopy, it had the mineralogy and chemistry we were hoping for, dominated by hydrated phyllosilicates. Those are clay minerals. They form typically through reaction on Earth, maybe with seawater and mantle rock. The iron oxide magnetite, which is also characteristic of aqueous environments. Lots of organic molecules, which feed that origins investigation and really were the driving motivation for the mission. And carbon in a mineral form called carbonates as well. So this is really what we expected to return. Here you can see a couple cameras. This is the SAM cam. And this is a side-looking nav cam. This is the shadow of the collector. This made contact with the asteroid surface at about 10 centimeters per second. And the disc that's at the end of this robotic arm is basically an air filter. And the concept is you push the filter down into the asteroid surface, you fire a gas bottle, open up a bottle of high pressure nitrogen gas, you use it like a leaf blower to push the gravel and the dust into that filter and then back away from the asteroid surface. So it's a touch and go. The plan was to be in contact for about 6 seconds. What we see here is that, first of all, the surface was very compliant. There was no resistance to the downward motion of the robotic arm. We penetrated very deep, about 50 centimeters, so almost the length of my arm, down into the subsurface of the asteroid, collecting sample along the way. And then as you look at the back away footage, if you noticed the shadow, the actual contact point is just off the field of view of this wider field of view image. This is like a crater wall that's being excavated from the contact, and then the thrusters are sculpting the plume. So it was a very large surface disturbance, surprisingly so, indicating low density on the order of 500 kilograms per cubic meter, which is about half that of solid ice and about 1/6 that of your average rock, as well as very low intergranular cohesion to result in that dynamic surface response that we saw there. We stowed the sample 9 days later on October 29th of 2020. And we could see particles up to 3 centimeters. They were a troublemaker. If you remember the story, there was material leaking out of the tag SAM. Because there was a large 3 centimeter stone that was jamming open a flap that was meant to keep the material in there. And we saw dust and lots of fine particulates during the collection. So we expected the collection to range from submicron particles up to 3 centimeters or so. With those minerals that I indicated, we added sulfides. Even though we didn't see them spectroscopically, we expected that they would be there cosmochemically, and they're not spectrally active, so there was no way to detect them with the instrumentation that we had. Based on all of that, we think that the material would be similar to type 1 carbonaceous chondrites, which are the most volatile rich. The CI chondrites have the distinction of having major element abundances very similar to the solar photosphere, representing, we think, the bulk composition of the protoplanetary disk. We did see rare exogenous material that looked like clinopyroxene material from asteroid Vesta. That is in our collection as a group of meteorites called the HED meteorites. So we thought maybe we picked up some of those. I mentioned that really low regolith density. In general, the grain density looks very low. The porosity looks very high. A lot of material properties on the surface that would not make it through the Earth's atmosphere. So we're thinking maybe we brought some stuff back that we haven't seen before. I'll show you why we think this, but we see large white veins of material throughout some of the boulders that we interpreted as carbonates. So we expected maybe we had some pieces of those veins and maybe centimeter scale carbonates. And then Bennu was famous for ejecting particles as an active asteroid on the order of centimeter scale. And maybe we had some material that actually was in orbit and then landed back on the surface. So these are all the things we were looking for. Flash forward to September 24th, 2023. Here's footage from that same nav cam that had the side view during tag, and that's the sample return capsule being launched towards the Earth. This is the limb of the Earth over here. This was about 4 hours before atmospheric entry, where we ejected the capsule, and it was about a quarter of the distance between the Earth and the Moon. So it had a long solo flight through cislunar space before it entered the atmosphere, which it did. And despite a wiring issue, which you probably all heard about, the main parachute deployed when it needed to, and it brought the capsule down for this gentle landing. We have this somewhat heartbreaking footage from the Air Force camera that was stationed on the ground, because we're about to land and the capsule goes behind this ridge. So we don't actually see the landing. You will see that we did land because the parachute deflates right there and collapses. And then, of course, we were on the scene very quickly. I was on one of the helicopters that was heading out to the site. I was part of the environmental sampling team, which was there to document the soil, the vegetation, the dust in the wind, any outgassing from the return capsule, just so we understood the environment, because keeping the material pristine, which means free from any interference from spacecraft components or from handling or from the recovery site, doesn't compromise our scientific investigation. So we got out there. It was great to see the capsule after all these years. It had been 7 years since I'd seen this hardware in person. And I like to say it was like greeting an old friend, right? Been on a long journey, 7 years out in deep space, billions of miles, a little charred and worse, for its passage through the atmosphere, but in pretty good shape and perched perfectly like an Olympic gymnast. It stuck the landing. It landed right there. You can kind of see it. It touched down there, so it tipped over and then back up, and just absolutely flawless recovery resulting. You can see the weather was really great. We quickly got it we flew it the next day on Monday, September 25th to NASA's Johnson Space Center. The US Air Force provided us with a fantastic C-17 transport aircraft for that ride. Very grateful for our military colleagues and all the support that they gave us. We came in the Utah Test and Training Range, which is a Department of Defense range run by the Air Force and the Army, and we worked with them extensively for months leading up to that activity. So it was really great. This is the special clean room at NASA's Johnson Space Center where the samples are curated. There's 2 different cabinets. In the back here is the canister, and I'll show you a picture. That's the aluminum housing that the sample collector was placed inside, kind of like a vault or a treasure box. So we had to process that, open that up, get the sample collector out, and then this is the tag SAM cabinet where the sample collector gets disassembled and access to the main sample is achieved. And we can document it and then distribute it from there. So this is the canister. So this is what we call the avionics deck. Back here is the canister lid. That was opened very quickly. Within a couple days of arriving at Johnson Space Center, there was a lot of news about not being able to open the capsule, which is wrong. The capsule was disassembled at Utah. The heat shield was taken off, the back shell was taken off, a lot of the batteries and things like that were taken out. So the capsule was opened immediately. The canister was opened very quickly at Johnson Space Center, revealing the tag SAM, which is here, about 30 centimeters in diameter, if I didn't give you the scale earlier on that. And then right away, we saw this nice fine ring of dust, and then a second ring of what we would call intermediate particles on the order of millimeter or so. And they have a distinctive pattern which matches the braided wire seal. So you can see here's a braided metal seal. And these intermediate particles somehow got pushed past the wall and got stuck in that braid. It's interesting to me why the fines were accumulating there and the intermediates made it farther. This was all under a nitrogen purge. So there was nitrogen gas blowing through here, which pushed everything to the outer edge. A little bit of a mystery, but the great part of it was we could sample this right away. So we collected material from right in this region and distributed it to the science team. And a lot of the results that I'll be presenting are from this, what we call the quick look sample. And then we also got into tag SAM, and there'll be some results from the main sample as well, especially the shape and morphology. So here are some of the particles that we got out from that quick look. Note that this is 250 microns or 1/4 of a millimeter. This is the largest particle that was in that collection. And you'll see this again because we did X-ray computed tomography analysis of it. And we have that data to present to you here. That's about a 2 millimeter size particle right there. So you can kind of get a sense of the scale of this. Lots and lots of sample. The amount of material that we released to the science team during this quick look phase exceeded that of the Hayabusa 2 mission over their entire sample analysis campaign. So as you'll see, we think we brought back on the order of maybe 120 grams. So we have a lot of sample to work with here. All right, so what did we get? Let's take a look. Remember what we predicted, those hydrated phyllosilicate clay minerals, carbonates, iron oxide magnetite, sulfides, and organic molecules. Here we're looking at an X-ray diffraction pattern. So we simply just took the fine powder, scan it over a range of angles with this cobalt K alpha X-ray radiation. And wherever the angle satisfies Bragg's law, which means that there is a relationship between the wavelength of the X-ray and the spacings of the atomic planes in the crystal, you get a big spike. So each one of these is a very specific distance of a crystal lattice. And when you add all those distances into one analysis, you can say, there must be the following minerals present because we know the crystal structures. So sure enough, we got phyllosilicates. You can see they've got some broad peaks here. They may have microscale crystallinity. They're very, very, very fine grained. They're kind of a strange mineral, especially the main one, serpentine, because it has kind of a wavy, fibrous form. So it doesn't make a nice compact crystal always. About 80% of the sample from this analysis looks to be phyllosilicates. We see the sulfides dominated by iron sulfides, about 10 volume percent. Here's our iron oxide, magnetite, and our carbonate. So pretty much the remote sensing spectral analysis from the spacecraft instruments and from the ground were accurate. We were able to predict the mineralogy of this really well. Of course, there's a lot more going on at the detailed level. So we took a lot of those quick look samples and right there at Johnson Space Center, and then also here at the Lunar Planetary Laboratory, we just started surveying what minerals are present in this material. So we have the main phases over here, the phyllosilicates, which look like they're mostly serpentine with some smectite. We have the magnetite. I'll talk a bit about the phosphates because those are the big surprise so far, magnesium sodium rich phosphates. Lots of different carbonates, the calcium carbonate, magnesium bearing dolomite, iron bearing brunerite, and then the main sulfide appears to be the sulfur rich pyrrhotite Fe7S8. We see lots of minor phases like anhydrous silicates, olivines, pyroxenes, plage, different iron, titanium, chromium, aluminum, magnesium oxides, a range of sulfides we haven't identified fully yet, but we see nickel bearing, probably a phase we call pentlandite, copper rich, iron rich, and zinc rich sulfides. So lots of work to sort out what's going on there. Some halides like sodium chloride, potassium chloride, which is exciting because that also is indicative of an aqueous environment. So a few minor calcium rich phosphates, and then some very reduced iron phosphides like schreibersite and andreavanovite. So a lot of different minerals present in the sample. These are probably, except for the halides, I would say, and maybe the sulfides, a lot of these anhydrous silicates, maybe some of these oxides, and the calcium rich phosphates are probably precursor material from the material that was aqueously altered to produce the phyllosilicates. They're very rare, but we're starting to see them as we look and search. So that'll give us a sense of what the rock was like before the aqueous system was in place, which altered the material into the water-bearing clay minerals and associated phases. And just some beauty shots. Thank you to Pierre. I think Hannacourt took all of these images right upstairs in our SEM. And the first four, the top three in this one are the different forms of iron oxide or magnetite. We see the framboidal occurrence. You see all these little crystallites here that group together, kind of like a raspberry or a framboise in French. So this is why we get a framboidal structure. We see plaquettes stacked. We see these radial forms. This is a vein that's had these magnetite crystals grow into it, and then some of them look like they've been etched, like there was a late stage corrosive action that etched away at the surface. Not all of them, like this one seems to have avoided it, whereas the one right next to it appears to be heavily etched. And then over here, we see the sulfides, very characteristic hexagonal morphology of that pyrrhotite. Lots of interesting examples of size ranges of this sulfide throughout the material. We do see lots of organics and carbonaceous material throughout. Some of it is macroscopic, like these veins of very carbon-rich material here. We see mineral aggregates that seem to have interstitial carbon-rich material and abundant nanoglobules. You can see here, this is half a micron, 500 nanometers size, these spheres of carbonaceous material. Sometimes there's components inside, sometimes they appear to be hollow. We also see diffuse unstructured organics kind of throughout the phyllosilicates. You can't really pin them down, but you get a carbon signal during analysis. When we put it into a mass spectrometer, there's this instrument at Johnson Space Center called the Micro L2MS. It's laser desorption, laser ionization. So the first laser desorbs volatile organics, and then the second laser ionizes it, so you can send it to the mass spectrometer and determine what its mass is and therefore what its structure likely is. And this is all we did here was take a small grain, a series of grains, kind of crush them on a plate to flatten them, and then put them into the instrument. Without even firing the laser, the sample is outgassing. All these different peaks are different organic molecules that are just coming off a freshly fractured surface from the sample. These are all what we would call polycyclic aromatic hydrocarbons. An aromatic hydrocarbon is one that has this six-sided ring here. If it's a single ring, it's benzene. And then when you have two, you get naphthalene, phenanthrene when you get three, pyrene when you get four. So Bennu has a lot of these native organic aromatic hydrocarbons that appear to be loosely bound and easily liberated from the material just by exposure of a new, fresh surface in vacuum. So the samples are definitely organic rich. We see abundant polycyclic aromatic hydrocarbons. When we do go in with the laser and do the desorption and the ionization, the spectrum looks almost exactly like the material that's just outgassing naturally. So you're just adding more energy to liberate material that's absorbed on the surface there. It does look similar to a very famous CI chondrite or gay, which fell 140 years ago or so, and is still by mass the largest sample of the CI chondrites that we have on Earth. It looks pretty clean, no signs of thermal processing. So the polycyclic aromatic hydrocarbons tend to get more carbon rich and hydrogen poor as they're heated and processed. We don't see really any indication of that, and no terrestrial contributions to the spectra as well. So I think we have a clean sample, organic rich, just as we hoped. Let's take a look at the bulk chemistry. So this is a famous plot. If you've taken cosmochemistry here at LPL, you should be very familiar with this. What we're looking at is a whole range of chemical elements. Over 40 elements were analyzed. I didn't mention it, by the way, but all the analysts that contributed data were listed along with their institution in the upper corner of the slides here. This came from the group at Washington University in St. Louis. And the elements are sorted in a very particular manner from what we call refractory, indicating that they're stable in solid material at relatively high temperatures under the conditions we expect for the protoplanetary disk, all the way down to volatile elements that stay in the vapor phase persistently to relatively low temperatures, in most cases well below the condensation temperature of sulfur, which is around 700 Kelvin, and down to icy temperatures like 150 Kelvin or so. So these are sorted from things that are most refractory to elements that are the most volatile. And there's a lot of other meteorite groups that are plotted on here, like CM chondrites, CO, CV, and CK. I won't go into all of these, what they mean. They're just different carbonaceous chondrite meteorites that are very well studied. This is Ryugu, which was the samples returned by Hayabusa 2 from the Ryugu asteroid. And then here we're just normalizing them to the ratio in CI chondrites. And you can see for most of the meteorite types, they're very enriched in refractory elements and very depleted in volatile elements. This is characteristic of carbonaceous chondrites, with the exception of the CI chondrites, which have the full complement of even the most volatile elements that are on this plot. They're typically depleted in noble gases and in major ice-forming elements like carbon, nitrogen, and oxygen. But all the lithophiles or rock-forming, metal-forming, sulfide-forming elements match the solar photosphere very well. This is a big result. So what this is saying is that Bennu has bulk solar abundances for all the elements except for ices and noble gases. This is a central data set to cosmochemistry, and I can tell you we agonize over every one of these elements. What is the abundance in the solar photosphere? What is the abundance in CI chondrites? Now we have a large reservoir of solar abundance material for analysis in our laboratories. We will nail the solar composition of all these elements because of the returned Bennu samples. So that's quite exciting. This is from the Tag Sam interior. So this was something after we pulled that material out. We started with bulk elemental analysis of the finds from the avionics deck. And I guess I don't have those. I might have pulled that out. They were a little different. They were enriched in a few elements like phosphorus and sodium. They were spiking above this line. That was giving us a hint of a very exciting chemical component, which I'll talk about later in the presentation. Okay, what about the ice-forming elements? They're not there in solar abundances, but they're very enriched in the samples. So this is the work done at Carnegie Institute of Washington. And you can see the hydrogen abundance is about 1 weight%, carbon approaching about 5 weight%, and nitrogen about 1/4 of a weight%. These carbon numbers are great. These are some of the highest values ever measured. In fact, the Carnegie analyst said this is the highest extraterrestrial material carbon content they've ever analyzed in their laboratories. It's right at the top edge of what has been reported for meteorites in the literature and above what's been reported for the Yugu samples, although there are smaller analyses, smaller grains that have been analyzed with higher weight percent carbon. But this is fantastic. This means we've got a very carbon-rich sample, solar composition for most other elements, so representative of the volatile element abundances that were in these hydrated planetesimals early in solar system history. We can gain some insight into how these materials fit into the astromaterials collections that we have by looking at the isotopes. And we're going to focus on the deuterium to hydrogen ratio, which we characterize as per mil, part per thousand, typically, variations from a terrestrial standard, in this case, ocean water. But you can see we've got D to H ratios of 288 to 344 per mil, pretty heavy. And then we look at the same kind of information for nitrogen 15 to nitrogen 14, and we see between 58 and 75. And we plot those two parameters versus each other, delta D on the x-axis, delta N15 on the y-axis. And you can see Bennu showing up here in a region that's unpopulated by other astromaterials. Here are the CI chondrites. The red are the CM chondrites. Here's another group of aqueously altered carbonaceous chondrites called the CR. Bennu's distinct from all of those. It's not far from Yugu, and then it's closest to a very interesting meteorite called Tagish Lake. This fell in the Canadian Arctic onto a frozen lake bed. It was collected very quickly. It is a complicated sample with multiple lithologies, but it has been postulated to maybe come from asteroids in the outer main belt, what we call D-type asteroids. And Bennu seems to be close to that in this isotope space. Bottom line is it looks distinct from other carbonaceous chondrites. It looks distinct from Yugu. So it is giving us some insight into material that we don't have into our collections. Of course, the gold standard for typing astromaterials and understanding relationship relative to other collections is oxygen isotopes. Oxygen has the benefit of having 3 stable isotopes, where hydrogen and nitrogen and carbon only had 2. So you can do what's called a 3 isotope plot, where you take the 18-16 ratio, plot it against the 17-16 ratio, and this is a classic diagram in cosmochemistry. Anything on Earth or from the moon would fall on this terrestrial fractionation line. So you can change these ratios. For example, if you evaporate a liquid reservoir, the heavy isotopes will tend to remain in the liquid and the lighter isotopes will partition into the vapor. And if you do that, the fractionation of 18 to 16 will be roughly twice that of 17 to 16, and you get a slope 1/2 line. If you're simply mixing components, you have a reservoir, say, of something very oxygen 16 rich, which would plot way down here, actually way down here, like for the sun, and you're mixing it with something, let's say on the terrestrial fractionation line, it'll fall on a slope 1 line. And a lot of our carbonaceous chondrite anhydrous minerals fall on that line. Bennu is falling up here. It's well off what we call the CCAM. We can renormalize with a parameter called cap delta 17, basically taking the terrestrial fractionation line and making it horizontal. And then you're just looking at the deviation from that line. And you can see, in fact, Bennu samples are distinct from the terrestrial fractionation line. That's good. It means we don't have a lot of contamination dominating the signal from the Earth. And it's distinct from most of our carbonaceous chondrites, although it starts to overlap. This is the best analyses of CI chondrites. Here's some other literature values, and we're starting to see potentially some overlap there. And you can see also distinct, but maybe getting close to Yugu as well. So of all the meteorite groups, it's falling closest in isotope space to the CI chondrites or related thermally altered chondrites. Okay, so that was kind of what we were learning from the quick look samples, placing it in isotope space, getting a sense of the bulk abundances, looking at the major mineralogy. But of course, the real goods were inside the tag SAM, and we couldn't wait to get in there. And you probably heard about the saga of the stuck fasteners, right? There was 2 screws, that we simply couldn't get unstuck with the tools that we had available. And by we, I mean the awesome processors in the curation facility at Johnson Space Center. They were going in with just a standard kind of screwdriver. It had to be non-carbon steel because we didn't want to shed any particles and have carbon contamination of the sample, meaning a kind of a soft tool steel. And the fasteners just wouldn't budge. And so we were going to write a press release and say, we're stuck. And then one of the processors simply took a spatula, and this is the Mylar flap that was stuck open, that was letting material escape after sample collection. And she's like, well, I can see the particles in there, Dante. And I was like, could you grab them with tweezers? And she's like, yeah. And I was like, well, why don't we do that? So I talked with Francis McCubbin, who's the head astromaterials curator there. I wrote him a long email about why we should do this. And he responded and he said, I had the exact same thought, and that's what we're going to do. So we're able to get a lot of material out of the TAGSAM head. So here you can see 4 trays. We call these our pizza trays. And the plan was TAGSAM would be placed above this. A baffle would cover these gaps, and then we would kind of just pour in 8 directions and get the TAGSAM material to fall into these different trays. Since we didn't have TAGSAM open, we couldn't do that. There was material that was sitting on top of the Mylar flap right when we flipped it over, and that material went into trays A1 and A2. And then everything we were able to grab with tweezers and scoops went into A3 and A4. And this went fast. Within a few hours, we had this material isolated from TAGSAM. We got a mass of 70.3 grams. The mission requirement was 60 grams. And they said, well, we could get more material, but we need to lift the TAGSAM, kind of tap it, get it to concentrate at one end, and we could go back in with our scoops. And I was like, no bother. And I said, put it aside. Get a team spun up to build a new tool. It's NASA after all, right? You should be able to figure out how to get a tool that'll work in this environment. You have tools that work in space, right? So let's just take our time, solve that problem. And this is more than we expected when we wrote the mission proposal. Let's just go down the science path. So we began allocating material across the world from this collection here. And the material that came to the University of Arizona was collected right in this region from tray A2 because I spotted a couple of cool grains. I'll show you one of them that I wanted to make sure we got into our laboratories here for analysis. But they, just to flash forward just a few days ago, last week, right? They got their tool designed and tested. We had an engineering unit of TAGSAM. It worked great. So they finally got TAGSAM open. So this is our latest shot of what's left inside there. You can see I had an estimate here. Mass remaining in TAGSAM was between 30 and 70 grams. And that looks about right to me when I look at that. I'm thinking 50 grams, probably a good estimate, but we'll see. We're hoping that we get this poured out by maybe the end of this week, although they're having weather challenges in Houston. So maybe next week we'll get the final mass from TAGSAM. But that's brand new. We haven't done anything other than look at that cool picture and get excited that TAGSAM's opened up. With the material that was in the 4 trays, we did a particle size distribution count to give us a sense of the nature of the collection. And sure enough, I didn't point it out, but we have one large particle you'll see right here. That's 3.5 centimeters, which is what we predicted. This is probably our troublemaker, right? The one that was propping open the Mylar flap and causing all those materials to escape. So that's here, the biggest particle, 35 millimeters. And then this is cumulative. So we see 2 particles bigger than 2 centimeters or 20 millimeters. That includes this one. And so 7 includes these 2, et cetera, et cetera. So we have over 1,000 particles that are greater than 0.5 millimeter. And we have about 28 particles that are greater than 1 centimeter. So a fantastic astromaterials collection, enough material to keep the community busy for decades into the future. Let's take a look at the spectra. So this was one of the aggregate samples taken out of the trays from TAGSAM. 2 different views here of the same data. One is absolute reflectance. So we're going from visible, 0.4 microns, out into the near infrared, 4.5 microns. This is about the range that our OVIRS instrument, the visible and infrared spectrometer, measured. You can see Bennu is in red here. This is the global average. So you can see what I mean by the blue slope, right? It's very subtle, but it does get more reflective as you go to these shorter wavelengths. There's a characteristic absorption feature here at 2.7 microns. That's indicative of the hydrogen-oxygen bond. That's those hydrated phyllosilicates. And then out here in the noisy 3.4 micron, there's indicative of carbonates as well as organic molecules. This is Nightingale, the site before we tagged, and then after we collected the sample. So it got a little less blue as a result, and it was generally higher reflective in these wavelengths. And then here is the sample, and you can see it's got the exact opposite slope. It's a very red slope, so its lowest reflectance value is at the shortest wavelength, and it gets more reflective. Definitely got the hydration feature and the organic feature here as well. And I just normalize these to the 0.4 micron to really show you the difference in slope. So here's Bennu and Nightingale pre-tag. Here's Nightingale post-tag. So it's getting redder, and then the return sample is even more red. So this is telling us something about space weathering. When Danny wrote the paper, the idea was that the space weathering drives you to that blue slope. And when we saw Nightingale disturbance, we saw it did get redder, and then the return sample is redder still. So it's an outstanding question. Where is the blue component? I don't know if we found it yet. Maybe we have. And then it looks like the freshest material tends to be dark. You can see really dark, and also red. So there's a spectral analysis, spectral interpretation still to go here. Okay, looking at the morphology of the rocks, we see an interesting parallel with what's on the surface of the asteroid. So here are some boulders. The scale bar is being blocked down here, but it's about this big. That's 10 meter. So we see a lot of the boulders have what we call this hummocky, kind of rough texture. You can see Gargoyle Saxum, Chinquilla Saxum, Boubry Saxum all show that kind of texture. And then sure enough, we see hummocky morphology in a lot of the large particles in the sample collection. Here's a 1 centimeter scale bar. I don't know why you would have hummocky textures at the tens of meter scale reflected at the centimeter scale. It's not obvious to me what that means. And I probably would have ignored it, except for the other kind of boulder that we see on Bennu are these very angular boulders, very sharp faces, clear angles. And sure enough, other particles in the sample are very angular in their morphology as well. This I can kind of understand, where you have some sort of maybe metamorphism that introduced a foliation or preferred planar direction, and that would break at small scales, and that would also break along those at larger scales. So that's interesting. Why you would get the hummocky texture to have that fractal pattern, I'm not sure. But the fact that we saw the angular lithology and we saw the hummocky lithology is the same distinction we see in the boulders in Bennu. It tells me maybe there's something important that we need to chase down. Here we can take a look at one of those angular ones. I remember I pointed this grain out early on. This was from the quick look sample, that 2 millimeter particle. And this is X-ray computed tomography, which allows, it's like a CAT scan of the sample that allows you to see the texture in the interior. And we can also do density filtering. In this case, we're going to filter out the high density components. They'll be red. And those are mostly the iron sulfides. And you can tell because you can see the beautiful hexagons throughout the sample. They occur in a range of sizes. They look like they're pretty evenly distributed throughout the phyllosilicate ground mass, and they have a range of orientations. So a couple thoughts come to mind. First of all, the fact that they're so well defined with this habit, this hexagonal habit, suggests when they were growing, there was nothing impeding their growth. So they were growing into free space, maybe crystallizing in the fluid. And the random orientations suggest that there was no preferred pressure or any kind of stress or force that was allowing them to grow in one direction versus another. So there's a lot of work to do to understand this population, their sizes, any variation with the size, their orientation distribution, try to understand how they crystallized and grew on the asteroid. Okay, and then the third type of lithology, I think, links back to these features we saw on the asteroid. Very high reflective veins of material, which we interpreted to be carbonates. When we looked at the OVIR spectra, we saw calcite, the calcium carbonate, the iron carbonate, the magnesium-rich carbonate and then the solid solutions, and they seem to correlate with these brighter boulders. This is, a meter scale bar here. There's actually one vein here and another one here that's a little bit hidden. We see it in other views of this boulder. So one of the things I was looking for was fragments of this, because we interpreted this in Hannah Kaplan's 2020 science paper to be hydrothermally deposited minerals. Like we see here on Earth, you see these carbonate veins typically have a hydrothermal system. As that system cools and evaporates, it leaves behind the carbonate minerals. And we've never seen anything of this scale in our meteorite collection, big meter or even chunky centimeter scale carbonate. So we're really hopeful we would bring some back in this return sample. And when I look at the biggest particle, and when I stretch on Photoshop, just the hue and saturation, you see it turns, this bright material turns kind of blue. There's another phase associated with it, turns kind of red. I have nicknamed this, against all mission policy, the heart of Bennu. Because it looks like a heart, and Pluto has a heart, so why not? So the fact that you could see it when we do that color stretch made it easy to see if there were other examples of this, what we're calling the modeled lithology in the material. And sure enough, doing that simple color stretch, you see here's a 1 centimeter scale bar for reference down here. This one, which I believe we're going to get allocated to the science team relatively soon. We don't want to touch the heart. To me, that's like the Hope Diamond from Bennu. I mean, that's just a precious sample. It would be a long time before we would think about getting into that, and we might not get to it as part of our sample campaign because we got all this other great material to study. You can see some expressions like small areas here. Looks like some sort of clasp maybe here, very sharp boundary. There's more of that red material. So it's definitely a component. And the fact that it's on the heart there, which is about 10% of that 70 grams by mass, indicates that it's an important component we need to understand. Fortunately, when we got that aggregate sample here at the University of Arizona, we had this particle in, note the 1 millimeter scale bar down here now. And we were able to then study it in more detail. So you can see it's all over the surface of this sample. When you look, this is the optical image. This is a scanning electron microscope image, and you can kind of see the material there. My son was in the lab when we were collecting these data, and he said it looked like alligator skin, which kind of has given me that sense of maybe that's what we're looking at here. You can see a piece broke off from here, and you can see it right here before it broke off, and you get a sense that there was maybe a vein right there that it fractured along, and it exposed that material here. So we'll zoom in on this to get a sense of its structure. But before we do that, we were able to measure its elemental abundances, or at least its elemental occurrences. And we thought this was going to be the carbonate, like, okay, centimeter scale particle, like the heart, covered in this high reflectance material. We saw those veins on Bennu. We thought those would be the carbonates. No carbon, no calcium, no silicon. Instead, we see high concentrations of phosphorus, magnesium, and sodium. So these look like magnesium sodium phosphates. We have confirmed the phosphate through Fourier transform infrared spectroscopy. If we zoom in on that box that I showed you on the previous slide, you can see here is what looks like the main lithology. And the reason I say that, some indicators, you see the little hexagons, which are the sulfides. When I see the little hexagons, and I also see the framboid magnetite. This looks like the clay-rich material with the embedded sulfides and oxides and minor phases, and that the phosphate looks like it was a vein or a crust or a surface skin. In fact, you can see this piece broke off from here, and it was kind of curved, so it was conforming to the underlying host rock. So we have some sort of depositional material, very strange composition. Not a lot of occurrences of this geochemically that I've been able to find. So this is our exciting result. When I was at AGU, I put out the call. I said, if anybody has seen something like this, we want to know and we want to talk to you. Fabian Kreller came up to me afterwards and he said, we just wrote a paper last year looking at the Cassini ion neutral mass spectrometer data as it flew through the plumes of Enceladus, and they were detecting sodium phosphate particles coming out of those plumes. And I was like, well, that's kind of cool. I looked at the paper. They did some really nice thermodynamic modeling of ocean chemistry. And in there, they conclude you'll get phosphates as in high concentrations in a residual fluid, say that's evaporating, and you won't make the calcium phosphate, which is the normal geochemical occurrence of this in meteorites, terrestrial rocks, igneous systems, because the solution is saturated in carbonate. And if the solution is saturated in the carbonate ion, when it precipitates, the calcium carbonate will go first. It'll take all the calcium out of the system, leaving the phosphate in solution. And then when it ultimately does condense, it grabs whatever cations are left, in this case, sodium and magnesium, which is the dominant one in the system. So this is brand new thinking, but maybe we're looking at a residue from a fluid that was saturated in carbonate. The phosphate became highly enriched. And then as the system, it must have been an open system and you were losing the water, this crust was left behind. So let's wrap it up. How did we do? Testing predictions. We said size range from submicron to 3 centimeters. Check. Largest particles, 3.5 centimeters. All of the phases that we expected, either from remote sensing or our cosmochemical knowledge, were present. We're definitely looking at a lithology similar to type 1 chondrites. We're not going to say it's a CI chondrite or a CM chondrite. There's enough differences to say that it's like those, but it's not necessarily maybe from the same asteroid. No sign of the igneous non-chondritic particles like the vestoids or the HET meteorites. Definitely properties distinct from known meteorites. We're just getting into the physical properties, strength and moduli. But already the magnesium sodium phosphate crusts are something we've never seen before in our meteorites. There's minor occurrences in the Ryugu samples. And in fact, those results were some of the ones that at first we thought this was contamination. We were just finding the little white chips in those quick look samples. But then Ryugu the Hayabusa 2 team reported them in Ryugu, and now we're seeing them all over. And no sign of monomineralic centimeter scale carbonates. So the centimeter scale particles are coated in phosphates. Does that mean the veins are phosphate? We're not ready to go there yet, but we're certainly not seeing large vein material like we thought. And not enough work done to know if we have the ejected particles. The search is ongoing for those. We are starting to see some space weathering signs on the surfaces of some of the stones. Okay, so what are the implications? First of all, we're definitely have hydrated, organic rich serpentinites from the early solar system. Serpentinite is what you call a rock that's dominated by serpentine. And on Earth, they form from CO2-rich fluids, biohydration and alteration of ultramafic rocks. That's what we think probably happened here. The ultramafic rock, we're still trying to understand by looking at those small remnant anhydrous minerals. Was it a chondrite? Did it have chondrules like we are familiar with? We're not sure yet. We're not sure. We can't say that it was a chondrite prior to turning into the serpentinite. There's a lot of fun comparative work to do with terrestrial serpentinites and the Bennu serpentinites, I think. The bulk elemental abundances are solar, except for the ices and noble gases. And so we now have this awesome, pristine reservoir for future chemical investigations. The spectra are distinct from the global asteroid, which has this negative spectral slope, making it a B type. It's more positive even than Nightingale, even post-sampling, and redder than the small craters. So there's still the outstanding question, what makes B-type asteroids blue? What is changing the red to the blue? Is it the phosphate? Maybe. We're still got work to do there. We see sample morphologies in the stones that are similar to boulders, indicating a fractal-like fracturing process potentially. If you know something about this, please come and talk to me because we're trying to learn. It's not mechanical weathering is not my area of expertise, but something interesting is going on to give us the 2 main lithologies. No evidence yet of the carbonate veins, but we see that the magnesium sodium phosphates are the main high reflectance phase. And we're working towards a fluid model right now. We're also thinking maybe it's igneous, unlikely, but it could be. Maybe it's a vapor phase deposition. That might be more likely. But right now I'm thinking fluid systems. That would make sense with the serpentinite. And that we're looking at an enhanced phosphate in the residual fluid based on the interplay between carbonate minerals and the solubility of the phosphate-rich phases. There was just last week a paper that came out in Nature Communications looking at phosphate-rich soda lakes on Earth. And of course, we're interested in the Enceladus plume results from Postberg et al. But what this shows us is that there are environments, both terrestrially and extraterrestrially, where you can get high concentrations of dissolved phosphates because of the carbonate-rich fluid grabbing all the calcium and not allowing it to bond with the phosphate. So we have a fantastic collection, lots of exciting science, lots of students here at the University of Arizona involved in the sample analysis. That's the one I think I'm probably most excited about is to see the students go to town on this. And we're going to be working on these for the next decades. And I think we brought back something really special, carbon-rich, hydrated serpentinites with this cool crust of phosphate that we're chasing down, and maybe sampling an ancient ocean world from the very dawn of our solar system. So thank you for your attention. I'm happy to take questions.
Okay, any questions for Dante from the audience? We'll take one in the room first.
We also have people online.
Anyone? Oh yeah, Christopher's got one. Do you want to see if there's ones online, Dante?
Sure. I think I can do that. Can't hear, audio not working. Okay,
yeah, Dante, great talk, really interesting. I was just wondering, have you observed any mechanical changes to the sample since they've been on Earth? So going from a microgravity environment to the terrestrial environment, some little fractures are developing, some of the material looks really jointed. Are there any plans to take some of the samples and just see whether or not they're compacting over time, or just if there are any changes to the density of the material while it's here? It's still probably small, but I was just wondering if you'd observed any mechanical changes, even though it's under nitrogen, there aren't chemical changes that have been affecting the samples already.
We have. So one thing to remember is it got shaken pretty hard during the entry, descent, and landing phase. The capsule came in at 12.4 kilometers a second. So there was a huge shock and then the shaking. So there was a lot of mechanical agitation before we got a chance to take a look at it. We definitely see a range of densities. There appears to be some really low density material that's very friable. Even with tweezers, it tends to disaggregate. So we have to kind of scoop it and very carefully handle it. And Andy Ryan, I don't know if Andy's here, but he's a staff scientist at LPL, and he leads the physical and thermal analysis working group. And yes, they're going to be doing lots of compression tests. And like I said, measuring the moduli, measuring the cohesion, seismic velocities. So we will be going after mechanical properties. There's no plan to watch the collection over time to see how it disaggregates. It's a good idea. We have talked about taking a piece out and just putting it under the microscope for time lapse and just seeing what the atmosphere does to it. We are already getting indications from our Hayabusa 2 colleagues that sulfates tend to grow. One of the characteristics of CI chondrites are big, white, crusty sulfates, which we're pretty sure are now terrestrial alteration products. So to me, the terrestrial alteration is something that we really want to understand and are thinking about experiments to do that properly. Thanks, Christopher.
Any other questions? Don't be shy.
In the back.
Oh.
Lauretta
got one. I'm making you run up the steps.
Yeah, thank you very much. This is just a curiosity. Are you planning to do infrared spectroscopy, say from 5 to 15 micron? That would be really cool. So we can compare with James Webb.
Yes, we are doing mid-infrared spectroscopy out to 50 microns. We already have some of that data. I mentioned the Fourier transform infrared spectroscopy at the microscopic level. So looking at individual particles, including that phosphate, which looks pretty interesting. But absolutely, we're going to cover the whole range of the instruments we had on the spacecraft. So we had OVIRS, which was 0.4 to 4.5 microns. And then we had OTIS, the thermal emission spectrometer, from 5 out to 50 microns. And we'll be characterizing at that level as well.
Questions about deuterium. What you were saying went by, you were talking about D to H, considerably greater than unity, where of course the cosmological ratio is like 10 to the.
Right. Well, those are per mil values, so it's part per 10,000 variation from a standard. So that's not an absolute ratio. So keep that in mind.
Yeah, so I guess my question was, how much is it adds chemistry and
Right. So one of the big puzzles is the source of Earth's ocean water, and the deuterium hydrogen ratio has been key. A lot of heroic effort has been done using astronomical spectroscopy to try to measure this in cometary, coma, or outgassing, and also in these meteorites. These look like more terrestrial, like similar to what we see on Earth, not what we're seeing in some of the comets, although the comet data is kind of all over the map right now. So, but remember, it's not a deuterium to hydrogen ratio of 300. It's 300 parts per 10,000 away from our standard. So
I have to see it written down.
yeah, it's isotope geochemistry jargon for sure. Back.
Knowing what you know now about the OSIRIS mission, is there anything you would do differently than the plans 20 years ago?
Well, yeah, I would have wired my parachute harness correctly. I would have built the right tool to remove screws early. I think that's just kidding. I mean, we tried to do all that, right? I think when I look back, the payload change I would make is that both our spectrometers were point spectrometers with like 4 milliradian, 8 milliradian fields of view. And Bennu's surface is so heterogeneous that I really wish I had an imaging spectrometer, like a CRISM kind of instrument, where I could see spectral variation at the level of the grains and boulders that we saw on the surface of the asteroid. Because we get a big average of each spot when we analyze the surface of Bennu, and it all looks the same when it's clearly, just based on the boulder morphology, a lot of differences there. So I would probably have changed that, and lots of other ones too, but I think that scientifically, that's the one. And then maybe flying the mass spectrometer. We had a mass spectrometer on there early. We did see particles. We see these samples outgas upon agitation. There probably would have been some interesting results from a mass spec. I know my team members who were pushing for that hate to hear it because we de-scoped it early on in the mission, but I might have fought, harder to try to figure out a way to fly that one. I think it could have provided some interesting insight at the asteroid. Sounds on?
I can project, it's fine.
Yeah.
Well, there's people online.
Oh, people online. I was wondering about the magnesium and sodium phosphates. Are they exclusively a surface phenomena, or do you expect to see them embedded within the core of some of the rocks, like the sulfides?
Both, I think. And we're not even sure it's surface because these could be freshly fractured faces and left that behind. So they could all be veins.
Okay.
They're just surface exposures now. I think the one that broke off that I zoomed in on the electron microscope, I think that was a vein, and that was exposed due to fracturing. We also see small grains embedded in the phyllosilicates, just in the bulk sample as you're moving on. Like, oh, there's a little phosphate right there. So they're kind of all over. And in fact, Jess Barnes happens to be one of the world's experts in extraterrestrial phosphates. So we're pretty lucky that my next door neighbor and the working group lead for elements and isotopes knows all about these kinds of materials. So her and I were just talking today about different ways we want to go after it. But we want to compare what we see embedded in the matrix to what we see in these veins or crust. Are they the same? Interestingly, we already have a sample that was put on the transmission electron microscope by a couple of our grad students here, and it looks amorphous. So there's no crystallinity to it, which is also quite interesting. So we need to see at what scale does that persist to? Is it amorphous all the way? Are there little crystallites? And are there trace phases that might be included in there as well? And I didn't show the spectra. The spectra of that material show a very deep absorption around that 3.4 micron region, which is characteristic of organics. So we're thinking they might be organic rich material as well. But Jess is leading a consortium. The team is kind of saying, okay, what are all the things we want to do on this material, and how much do we have, and how do we go from least destructive to most destructive analysis to get the most information out of it?
And are these phosphates more fragile than the surrounding rock? Like if
Seem like it, yeah. It's definitely.
crumble?
When you look at the texture,
Sorry, I was futzing with it. That might have been.
oh, did you play with this? Okay, there you go. There. Oh, here. It's highly fractured. It looks desiccated to me, right? Like it probably was a hydrated phase and it's lost its absorbed water and shrunk and fractured as a result of that. I don't know if that happened on Bennu due to surface exposure or just 4 billion years of time, or if this was something that happened after it arrived here on Earth, because it was under dry nitrogen. It still is under dry nitrogen. But to me, it looks really fragile, and just the way it fractured and broke here just gives you a sense of it's barely hanging on to the host rock that it's connected to here. And probably why we never see it in the meteorites, right? It would have broken, anything coming through the atmosphere would have broken along these planes, and I imagine this material would volatilize really rapidly. So I don't know. To me, this is the most exciting thing. I did a lot of work on phosphorus in my early astrobiology research with one of my grad students back in the early 2000s. So to see phosphorus showing up as the surprise is really cool. So yeah, lots more to come on this material. Question online?
We have a question online from Alfred. Can you explain your ancient ocean world comment? Was Bennu part of a much larger asteroid-like series?
Yes, thank you. It's speculative at this point, so I don't want people to get too excited, but it's what I've been thinking about. So absolutely, Bennu was part of a much larger asteroid. Maybe not as big as Ceres. When we look at the asteroid families in the main belt that we tie it dynamically back to, we're guessing 100 to 200 kilometer sized object. That was the parent of Bennu. And it must have been very volatile rich because we see the serpentinites, we see the carbonates and the other phases that are indicative of that. And then we see this phase, this phosphate, which we're seeing geochemical environments, Enceladus, the soda lakes, where the way you can enrich a solution in phosphate is to be saturated in carbonate. So maybe we're looking at a solution, whether it's a global ocean or a pocket in the parent body, we're not sure yet. But one of the things we want to do is try to get a sense of the scale of the fluid system, how much concentration of phosphate you would need to produce this, and what can the trace elements, isotopes, geochronology, organic chemistry help us understand that environment better.
Any other questions from in the room? Yep.
So my understanding is that the OSIRIS-REx craft is heading to another asteroid, Apophis, I think. So how are you expecting that asteroid to differ from Bennu? And you mentioned, like, with your point spectrometers, how they have a small field of view. So are you expecting the surface of this other asteroid to be homogeneous or heterogeneous?
Well, I'll do a short answer, then maybe hand it over to Danny for the long answer. The short answer is, you're right. The OSIRIS-REx spacecraft, after it released the capsule, remained in space. We did a deflection maneuver, so we didn't follow the capsule into the Earth. And NASA approved an extended mission called OSIRIS-APEX, the Apophis Explorer, targeting another near-Earth asteroid called Apophis. I am not the PI of OSIRIS-APEX. I have handed the reins over to Professor Danny Della Justina. So Danny, do you want to answer the questions about what you think you're going to find at Apophis? Because I'm just here for the ride at this point.
Sure. So Apophis is quite different from Bennu as far as it's all of our data from ground-based spectroscopy. So we know that it's more analogous to other stony asteroids, S-type asteroids, which means instead of being dominated by, these water-bearing phyllosilicates, it's probably dominated by higher temperature forming minerals like olivine and pyroxene, the types of things that on Bennu might have gotten aqueously altered to form those clays. So we think it will look different. We had to demonstrate to NASA that our payloads will be able to detect all the interesting spectral features, and the reflectance of Apophis isn't going to, blow out any of our the dynamic range on our cameras because it's much brighter as a result of probably not having as much carbon as Bennu, if any. As far as the spectrometers and their field of view, I will say Bennu is the person who studied color across Bennu. It is unusually heterogeneous, even compared to other asteroids, even other carbonaceous asteroids like Ryugu. So it was quite unique in that it has what we think are a couple different types of lithology, and there is a lot of surface variability in its color and composition. I don't know if we'll see the same thing on Apophis, but if we do, we'll repeat what we did at Bennu, where we correspond our color data with our spectral data to try and bring those compositional inferences down to smaller size scales.
All right, let's take one more question. We had one up front here. Front row.
So I don't know this science very well, but I was wondering if maybe you guys had thought of rehydrating it or trying to reverse the process.
I have thought of that, just like, in my dream, kind of like laying at night. To me, it's going to be such a rare component. We got to be very careful about the experiments we do. But yes, I've thought about that. Would it just dissolve like a salt crystal, or is it resistant to the hydration? Is it like a desiccant? It would just suck all the moisture into it, and like, one of those toys that you get with the kid, the sponge or whatever, that grows to 3 times its size or whatever. So yeah, but none of that's official. Like we haven't. Jess is kind of running the show on the phosphate.
Won't be
plan.
licking it.
Yeah. We got the phosphate expert here. I said, and she said, I want to write an abstract about this particular particle. I said, yeah, the deal is you got to lead the consortium within the team to kind of think about the best way to analyze the material. So we're constantly shooting ideas back and forth, sending her papers, like the Soda Lake paper that I found over the weekend. We're still formulating the best way to go after this, but there's some key things we need to do. The elemental abundances, the crystal structure, spectra, organic abundances, and distributions. So we know what we need to do. The question is, what's the best way to do it? And then how do we test these models? I mean, quite honestly, if we do have a residue from an ancient ocean world, that's huge, right? I mean, that's like a big, big science result. So we want to make sure we're very careful about evaluating all the possible formation mechanisms, see which ones make the most sense.
Wow.
Right.
What a start to our spring colloquium series. So let's give Dante a big round of applause.